All right, so the number one in the book, we have the function, and I want to write it the same way they have it. F of x equals 1 over x. And what I want to do first, it says find the derivative of the given function at the indicated point. I'm going to ignore the at the indicated point. Let's go ahead and find the derivative of this first. Let's go ahead and generalize it, and then we'll put 2 in for x to do that. You wouldn't have to do it that way. In fact, the way it's really asking to do it in the book, it's asking you to find the derivative at that point as you compute it. So let me write that out very quickly here. But I'm not going to do it this way. So the slope of this function when x equals 2 is going to be equal to the limit as h approaches 0 of, okay, it's going to be f of what? F of a plus h, which would be what? 1 over
X plus h.
Okay. But what are we putting in for x?
A.
Okay, so if we're doing it the way, if we're doing it the way they're asking for in the book, without generalizing, just finding it at that point, we would plug in 2 for a, and we're finding the limit then as h approaches 0. So it would be 1 over 2 plus h minus 1 over 2 all over h. And we would evaluate that limit. If you let h approach 0 and you try direct substitution here, you would get 1/2 minus 1/2, which is 0, over 0, and that's going to tell you you're going to have to do some manipulations there. Okay, I would actually like to get a more useful formula to actually compute the derivative and then plug in the point. So to do that, we'll use the definition we got yesterday, which was this. Let me go back here. So the derivative of the function is equal to the limit as h approaches 0. Can you guys finish this for me?
1/2 minus 1 over.
Well, let's write out the definition first, and then we'll plug the stuff in. So f of x plus h minus f of x all over h. Okay? Have I beat this into you enough that you're getting to know it?
Yes. I thought it only asked for it at one point.
It did.
So why are we using it?
Because I want to practice doing it this way. So what I just set up in the maroon ink up there, that's what you would have done to do it at that point.
Why don't you do the f of x minus f of a over x?
So in this particular example, since f of x is 1 over x, this will equal the limit as h approaches 0 of f of x plus h would be, if we put x plus h into the function here, what do we get? 1 over x plus h minus 1 over x all over h. Okay, again, if we tried direct substitution here, we would get 1 over x minus 1 over x, which is 0, over 0. It's not going to work. We have to manipulate. When we have fractions, just one second. When we have fractions, the best thing to do is to either get a common denominator or multiply the top and the bottom to eliminate some stuff. Okay. Continuing here, how could we deal with the fractions that we have here? What could we do? Okay, yeah. So what I would do here is multiply by the common denominator. I would multiply the top and the bottom here by x times x plus h. Okay, so I have to multiply. If you do it on top, obviously you have to do it on the bottom. Otherwise, you're changing the value of your fraction. So by doing this, what we're going to do, what's going to happen is we're going to lose the x plus h here because it'll cancel when we multiply, and we'll lose the x in the denominator here because it'll cancel when we multiply. So when we do that, we still have a limit because we haven't been able to plug 0 in for h yet. What are we going to get when 1 over x plus h is multiplied by x times x plus h? What's going to cancel? The x plus h's. So what's left? X. Okay, and then we have minus. And the x's will cancel here, right? So we're going to have the x plus h left. Be sure that you put this in parentheses, otherwise your negative won't distribute and you've got something just a little bit wrong. And then on the bottom, I'm just going to leave it factored for now. So we have h times x plus h. There will be times when it will be more useful to distribute that. There will be times when it's better to have it in a factored form. Until I know which one's going to be better for me, I'll just leave it in the form that it's in, so that I don't end up doing more work than I have to in the end. What's going to happen up top? Yeah, the x's cancel each other out, right? So we're left with an h up top. I'm sorry, negative h. Yep, and that's really important here. Remember I said we needed to distribute, right? So we still have the limit as h approaches 0 of negative h over h times x plus h. Okay, now there's only one other thing we have to do here so that we can plug it in directly. We still can't, because if we did that, h would be 0 on top, h would be 0 on the bottom. We still have 0 over 0. But what's going to happen? The h's cancel. So we cancel this h. We're left with negative 1 on top. The h cancels there. And can we use direct substitution now? Yeah, if we do that now, if we put 0 in for h here, I can drop the limit because we're plugging it in. We get negative 1 on top. And what do we get on the bottom? What did you say? X squared. Did everybody see how you got x squared? Because we have the x here, and then x plus 0 is x, so we have x times x, which is x squared. Okay, now, that's the derivative of 1 over x. So the function 1 over x has the derivative negative 1 over x squared. Now, if I want to know what the derivative of 1 over x is at 2, so the question actually asked for this. I want to know what the derivative is at 2. All I have to do is plug 2 in for x here, and I get negative 1 over 4. Okay. The nice thing about doing it this way is if I want to know what the derivative is at 3, then I put 3 in for x. If I want to know what it is at negative 7, I put negative 7 in for x. So I can use this formula here to find the slope at any x value very quickly. Where if I had used that other definition, the one from last chapter, we would have been restricted to each point every time we evaluate this limit. And the limit would be about the same amount of work each time. So we would have to repeat all of those steps for each point if we wanted to use that other definition. Okay? Does that make sense? Okay. Are there any other ones from 1 through 4 that you want to see done? Okay. I want to do one that I actually put on your test because I thought it was a really fun one. So we'll say that f of x is the sine of x. And what we want to find here, what I would like to do is find the derivative of that function. And we're going to use the definition to do it. So how should I get started here? Gesundheit. Yes?
Wait, do we want to find it at one point or multiple?
Everywhere.
Okay. Hold on.
Okay. Yeah, we're going to use that same limit, right? So the limit as h approaches 0 of f of x plus h, which is sine of x plus h, minus f of x, sine of x, all over h. I think you guys are probably noticing a pattern here, but let's go ahead and try direct substitution. If we try direct substitution, we get the sine of x here minus the sine of x here, which is 0 over 0. Okay? When we're using this definition of the derivative, we always get 0 over 0 to start with. And the reason is this difference quotient here, this part right here, is the slope formula for 2 points that are on top of each other. And so our rise is 0, our run is 0, so we get 0 over 0. So our job now is to manipulate this so that we don't get 0 over 0 and we can evaluate this limit. So, any ideas what we can do? You guys remember the identity? By the way, I'm not going to make you memorize identities like that. If you need to use it, I will give it to you. Do you remember it?
Isn't it like sine of x times cosine of h plus sine of h cosine of x?
Yes. Good. So the sine of x plus h is equal to this, and that's just a trig identity that, like I said, if you needed it for a problem, I would give it to you, at least on a test. Okay, and then we still have our minus sine of x, and we're still dividing by h. You guys could probably guess this, but if we put 0 in for h right now, we would still get sine of x here times 1, because cosine of 0 is 1, plus the sine of 0 is 0, so it doesn't even matter this cosine of x here. So we're going to get sine of x plus 0 minus sine of x, and we still have 0 on top, right? So we're still going to have to make some changes. All right, so what I want to do now is split it up. We're going to actually split this up into 3 separate limits. There's a property of limits that basically says we can split up the limit of products is equal to the product of limits. The limit of a sum is equal to the sum of the limits. So what that's saying is if I rewrite it, and I'm going to do this first. Oh, that's way too big. Okay, do you guys see what I did there? So I just split it up into 3 terms. Now, what I did is I split it up into separate terms, so I need the parentheses here to show that we're taking the limit of that whole thing. But we can take the limit of each one of these. So I can find the limit of this, the limit of this, and the limit of this, and add these two together, subtract this one, and we're going to get the same answer. So I don't have to do it all together. I can do each part by itself. Okay? So looking at this first part here, this first term, what is the limit as h approaches 0 of the sine of x? Sorry. The sine of x times the cosine of h over h going to be? Well, what's going to happen here? Cosine of h is going to go to what? As h gets really close to 0, that's going to be really close to 1. So I'm going to just get rid of that. That's a 1 there, so it's a sine of x times 1. Does that make sense what I did there? Okay. In this term right here, the sine of h is going to go to 0, but I can't get rid of that because then what we're going to get is 0 over 0. And we have to manipulate, right? We have to make some changes. So I could do it here. Since I know the values are going to be 1 and it doesn't really affect this, I couldn't do it here because we still have 0 over 0. All right, now what do you notice about this term and this term? They're opposites, right? So what's going to happen to those? They're going to cancel each other out. So what we really have now is the limit as h approaches 0 of the sine of h. I'm going to keep it in blue. The sine of h times the cosine of x all over h. Yes?
Why can you plug in the 0 on the cosine h on top, but not the h on the bottom?
Because then we would have the sine of x divided by 0.
But it's okay to plug in the h on 1.
Mm-hmm.
Right? The 0 on 1 h.
Yes, and that kind of goes back to what I was talking about. That's a good question. So the question is, why were we able to plug it in here, but not here yet? And to answer that question, this limit is equal to, and this is going to be kind of a lot of writing here, and we try to avoid this just for simplicity's sake, but since we have a sine of x times a cosine of h over h, the limit of the product is equal to the product of the limit. So what that means is this is equal to the limit as h approaches 0 of the sine of x times the limit as h approaches 0 of the cosine of x all over the limit as h approaches 0 of h. Do you guys see how I got that? So just each of these factors here, the sine of x and the cosine of h, I just gave their own term. And then this number in the bottom in the denominator here, I gave it its own limit also. So any limit that we have that's multiplying, adding, subtracting, dividing different terms or different factors, we can split up into separate limits. Okay, so what that means is, and this should be an h here, shouldn't it? Sorry. What that means is I can evaluate different parts of a limit when it's convenient for me, which is really nice. I can't do this part yet. I can't do this yet because I end up with a 0 in the denominator. I can do this because I know this limit's just 1. Does that make sense? So to make a long story short, you can evaluate parts of a limit when it's appropriate or when it's convenient. Just be careful that you don't do it and then end up with some indeterminate form like 0 over 0 or infinity over infinity later on because you did that. Which is why we're hanging on to this 0 in the denominator here, because we're going to need that to cancel with the 0 in the denominator over here, basically. Does that make sense? Okay. Good question. So moving back to this, we've got this right here. Now, earlier when we had a sum in the numerator, we can split it up into separate terms with h in the denominator. If we're multiplying in the numerator, then we don't need an h in the denominator for both factors. And here's what I mean by that. This limit is equal to this. Everybody see how I got that? We okay with that? Okay. Just like I did before, I can split it up and find the limit of each part separately. The limit of, as h approaches 0 of the cosine of x, since there's no h's in here, it's just the cosine of x. Okay, h doesn't affect this at all, so this is cosine of x whether h goes to 0 or goes to any other value. It's just the cosine of x. This limit is one that I gave you a couple weeks ago. It's one that we looked at the graph of, and I said, we don't know yet how to find this limit, but it's one that you need to know. Do you guys remember what it is? The limit as h approaches 0 of the sine of h over h is 1. So at this point, we can... we're actually not going to use direct substitution. We're just going to use a limit that we know. So we're not really plugging h in for this part. But we can evaluate this limit. That's going to be 1. And we can evaluate this limit. That's going to be cosine of x. And so we get cosine of x. So the derivative of the sine of x is cosine of x. It's kind of fun, isn't it? Sure. If you say so, Mr. Betts. Anytime we're dealing with functions like trig functions or exponential functions or, I don't know, other types of functions, any function that's not a polynomial function, we're going to end up doing stuff like this, where we're going to have to use identities that we know or use properties of, say, logarithms or exponents that we know to be able to evaluate this. We are going to come up with a rule, and I think most of you know it by now. It's called the power rule for polynomials that will allow us to find the derivative of a polynomial very quickly without going through all these steps. Okay? Any questions about this? The methods that we're using here, finding the derivative using the definition. Okay, this is actually something that you'll need to know for the AP test, mainly because on the AP test, what they like to do is ask a question that asks you to, for example, evaluate a limit like this. They'll usually ask you one where you don't necessarily know the identity for sine of x plus h, and you have to recognize that this is actually the definition of the derivative of sine. And then you should be able to recognize this limit then as being equal to the cosine of x because it's just the derivative of sine of x. So you need to be able to recognize the definition of the derivative because they'll give you some problems where you evaluate limits using that definition. Okay. I do want to show you real quick. It's the exact same definition, but it looks just a little bit different. And I'll write it out here first. And then I'll tell you why we would write it like this instead. And basically what I'm doing here is I'm replacing h with delta x. So the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Now, why might we write the definition like this instead of using h? What does delta x mean? The change in x, right? If you remember the slope formula is just the change in y over the change in x, right? And the derivative is the slope of a function. So what's happening here in this formula that I gave you, we have delta x in the denominator just like we have in the slope formula. The change in the values of the function here is the change in y. So this right here, this difference quotient, is just the slope formula, just like we had with the h. We use the variable h a lot of times because it's simpler than delta x. So why might we put delta x into a formula like this? Why might that be useful or practical? Any ideas? You sleeping with us? Okay. Okay, I'll answer the question for you. Delta x is more descriptive than h is. So by putting delta x in there, it's telling us what it actually means. It's not just some variable, but it tells us what it means. So if we look at a picture of a graph, I'm going to draw the same picture I've drawn a few times before. So we've got a graph with a function in it, and we're looking to find the derivative of the function at some point. What we're doing is we're going to pick some x value, and in the past, we've called the distance between these 2 points h. If we just call this distance delta x, which is more descriptive, that's the distance between the two x values, then this second x value would be x plus delta x. And then what that means is we're going to have f of x here and f of x plus delta x here. And then to find the slope of that secant line, it would be f of x plus delta x minus f of x over delta x plus x minus x, which gives us delta x. Okay, and as we make this distance closer and closer to 0, as this limit suggests, then we get closer and closer to a tangent line rather than a secant line. So it's exactly the same thing. It just looks a little bit different. It's just using different terminology, basically, or symbols for that distance. Does that make sense? So don't freak out if you see a delta x in something instead of an h. It's the same thing. Okay. I would also like to look at some of the problems 5 through 12. If there are any in particular, you can shout them out, and I'll help you out with it. That we want to find the derivative at a point using that alternative definition of the derivative. Uh-oh. Which one do you want?
Number 7.
Okay, cool. 7. Is that the one with the square root?
Yeah.
Of course it is. All right. So we have f of x equals the square root of x plus 1. And we want to find the derivative of f at what point? 3. Okay, this time we're not going to generalize using the definition of derivative at a point. We'll just go ahead and plug the point in. So the derivative of the function at 2 is going to be the limit as, shouldn't be 2, should it? You guys just told me that. Is going to be the limit as x approaches 3 of what?
Square root of x plus 1.
So we do f of x first, so it's the square root of x plus 1. We just use the function minus
Square root of 3 plus 1.
square root of 3 plus 1, which is
2.
square root of 4, which is 2, right? Here, let's do this. All over
X minus 3.
x minus 3. Okay, and square root of 3 plus 1, that's just going to be 2. You guys remember how to, question?
We need to worry about the plus or minus.
Oh, with the square root? No. The square root's always going to give a positive result. It's only when we're solving equations that we have to worry about that. Good question. Okay, do you guys remember how to rationalize a denominator using a conjugate? Yes. What is the conjugate of the numerator here? Okay, sorry. I probably should connect the dots there. So if we try direct substitution here, we put 3 in for x here. We get 2 minus 2 is 0 over 3 minus 3 is 0. We get 0 over 0, right? Which means we're going to need to make some changes. You know how to rationalize a denominator and get rid of a square root. That's going to be something that we can use, or an idea that we can use to get rid of the square root in a numerator also. So what we need to do here is we need to make some changes. We just need to algebraically make some changes. So what we're going to do is we're going to rationalize the numerator. You've never done that before, have you?
Nope.
Okay. Rationalizing the denominator is, honestly, it's kind of an archaic thing to do. You had to do it before when you were making computations using tables out of a book rather than a calculator. So you had to do it before computers were involved to find numeric answers for square roots or quotients involving square roots. But it is really useful in calculus because it allows us to change the way a function looks. So just for the numeric computation part of it, it's really useless these days. It's one of those things that you learned earlier in school and there's really no point to it until now. So now rationalizing a denominator or rationalizing a numerator can be really useful for you because it's going to allow us to change the way this looks. So what we're going to do here is we're going to multiply the top and the bottom by the conjugate of the top. What is the conjugate of the top?
Square root of x plus 1 plus 2 plus 2.
Okay, cool. You guys are good at that. And most of you are awake. All right, so this is going to equal the limit as x approaches 3 of, now, since we're multiplying by the conjugate here, the middle term is going to drop out. You guys remember that? So basically we have to multiply the first times the first and subtract the second times the second. Yeah, you remember that? Okay, so what is the square root of x plus 1 times the square root of x plus 1?
X plus 1.
All right, and subtract 4. Okay, and then our plus 2 times the square root of x plus 1 minus 2 times the square root of x plus 1, those middle terms, those drop out. They cancel each other out. In the bottom, this is another example of one where I don't know yet if I'm going to want to distribute this or not, so I'm not going to yet. And some of you may be looking far enough ahead that you see that we don't want to. But in the bottom, we just have x minus 3 times the square root of x plus 1 plus 2. What's going to happen next? Yeah, on top, x plus 1 minus 4 is the same as x minus 3. So that is going to cancel with our x minus 3 here. And remember, this only works, we can only do this because we're taking the limit as x approaches 3, so we know x is not equal to 3. If x could equal 3 here, we couldn't cancel these out because we would be dividing by 0. Okay? So when we do cancel those out, we get the limit as x approaches 3. What's on top? 1 over square root of x plus 1 plus 2. And now we can use direct substitution. I know I'm not going to get 0 over 0 here because I have 1 on top, right? So when I plug 3 in here, what do I get?
2 plus 2.
Yeah, the square root of 3 plus 1 plus 2, and that's going to be 1 over 2 plus 2, or 1/4. So, you guys remember when I said yesterday that the calculus part's actually going to be pretty easy, and it's the pre-calculus stuff that might be kind of difficult? This is a good example of that, where the calculus part is really the part here where we're plugging 3 in for x. And I know that sounds silly, but that's the calculus part, setting it up and then evaluating the limit in the end. The pre-calculus stuff where we're manipulating the expression here, this function, that's all pre-calculus stuff. That's all stuff that you've learned in the past, and you just have to learn different ways or recognize different ways that you can manipulate the functions to be able to evaluate those limits. Okay, are there any other ones in that section that you want to see done? Vimmel? 5. 1 over x. Okay, we already did 1 over x, didn't we? All right, so f of x equals 1 over x, and we want to know what the derivative of that is at 2. Hey, we already did that too. So when we get an answer, we'll be able to check to make sure we did it right. Now, this is a different method that we're going to use, so it's going to look a little bit different. Right, Vimmel?
Yeah.
Okay, cool. So the derivative of the function at 2 is going to equal the limit as x approaches 2. We're approaching that x value now, right? Of what? What goes on top? 1 over x minus 1 over 2 all over x minus 2. Okay? We good with that so far? Okay? I'm glad Evan is, at least. Now what? Okay, multiply the whole thing by 2x over 2x. So we'll multiply by 2x over 2x. So that's going to give us the limit as x approaches 2 of, multiply 1 over x by 2x, and what do we get? 2, and then minus x over x minus 2 times 2x. Man, these look really similar. What's the difference between them? They're opposites of each other. So 2 minus x is the same thing as negative 1 times x minus 2. You guys agree with that? Okay. So if we rewrite that on top, is it okay with you if I just erase? I know I'm eliminating some of the work I did here. But we get the opposite of x minus 2 over all of that. Then what's going to happen? X minus 2's are gone. We get negative 1 on top. So this is the limit as x approaches 2 of 1 over 2x. Sorry, negative 1, which is equal to, plug it in, negative 1/4. And that's the answer we got with number 1 also, right? Does that make sense? Cole's having fun. Any other ones you guys want to see?